theorem. So this is it here. We have z is a complex number expressed in polar form as the modulus of z times cis of theta. Then z to the n, okay, where n is some power, some real number that's a power. We can simplify to modulus of z to the n and n times theta. So here, when you've got something like this, if you put that in your calculator, okay, it'll crunch out something in Cartesian form. So we'll spit it out in Cartesian form. And what we're going to do is we're going to convert it to polar form, and we're going to apply Demoivres theorem. So if I've got 1 plus I root 3, we should start. You're starting to get the hang of it. If we define that as z, all right, z is 1 plus I root 3, then the modulus of z is 2. All right, so it's the square root of 1 squared plus root 3 squared. That's the square root of 4, which is 2. And the argument of z, we can use our calculator. But again, like with a bit of knowledge of the unit circle, we've got root 3 at the top and 1 at the bottom. It's going to be pi on 3. Okay, nice. Yeah, we've seen that one. You see the same ones start to pop up a bit. Okay, so we've got this complex number in polar form. So what it is 2 cis of pi on 3 to the power of 7. Okay, so there are 2 ways of representing it, in Cartesian form and in polar form. Alright, so all we have done so far is express it in polar form. Okay, now let's apply Demoivres theorem. So we're going to have 2 to the power of 7, okay, that's this part here, modulus of z to the power of 7, times cis of n times theta. So that's going to be 7 times pi on 3. Alright, we'll simplify. 2 to the 7, cis of 7 pi on 3. And let's just do one more thing as well. Okay, cis of 7 pi on 3. Okay, like I'm probably going to accept it like that. Let's show you how else it could be written because it still can be simplified. Cis of 7 pi on 3, that's 6 pi on 3 plus pi on 3. Yeah, which is 2 pi plus pi on 3, which is 128 cis of pi on 3. Okay, so what's the relationship between this complex number and this one is that they have the same argument, it's just dilated by a scale factor of 64. Is it like 2 to 7? Okay, let's move on to 2 unless there's any questions about that one. Okay, so we've done these proofs before. We've done some of these proofs using when we were in further trigonometry last year. So we have seen this before, but today we're going to use complex numbers to do it. And in particular, we're going to use Demoivres theorem. So what we're going to do is we're going to go, if I have cos of 3 theta plus I sine of 3 theta, okay, that would be cis of 3 theta. Alright, cis of 3 theta. Now we are only interested in the real part of it. So we're going to perform this expansion and apply the theorem, but we're only interested in the real part because cos of 3 theta is the real part. Okay, so we're going to apply the inverse of Demoivres theorem here. So we're just going to apply it backwards. If we have n there, okay, then one way we can express that is cis of theta to the power of 3. Alright, so we can go back the other way. Okay, so now that we've applied the theorem, I'm now going to substitute this back in. Alright, so I'm doing this in an elongated manner, but that's okay. We've got cos of 3 theta plus I sine of 3 theta to the power of 3. And we've got to perform that expansion. Okay? And so this is one that we do suppose that you can do using Pascal's triangle. So I'm going to do it reasonably quickly, and I think we've all got a pretty good grasp of this by now. so using Pascal's triangle. That's what a cubic expands to. And what we need to make sure when you're performing this expansion, right, is that I sine 3 theta, that the whole thing is squared, okay, because that squared needs to distribute to the I as well, because that is going to affect our result. Now let's process this a bit and simplify it. So what that's going to give us, if we go, that's going to stay as it is, cos to the power of 3 of 3 theta. Here we're going to keep that cos. By looking along here, what I'm seeing is that this is one of the imaginary parts. So I'm going to pull that I out the front. And I want to be very deliberate. This is a real component because there's no I. This is an imaginary component because there is one lot of I associated with it. And that's 3 cos squared of 3 theta, sine of 3 theta. Okay, with this one we have I squared. Now I squared becomes minus 1. So that means this part is going to be take 3 cos 3 theta sine of 3 theta squared. Alright, so that's a real component because there's no I. The I squared has become minus 1. And this part here is when we have I to the power of 3. Alright, that's going to be minus I. And you can just work that out, but it's one we should remember that it's cyclic. But I to the power of 3 is minus I. And we have sine to the power of 3 theta. Okay, so let's remember I said we're interested in cos of 3 theta, which means we're only interested in the real component. So the real component are these two, because both of these ones have I involved. So I'm just like let's focus on real component. All right, so we've got cos power of 3 theta plus say 3 cos 3 theta times sine to the power of 3, sine to the power of 2 theta. Sine to the power of 2 of 3 theta. That's true. Alright, so we get to this stage and then there's just one substitution that we need to perform, and that is that sine squared. Remember this relationship, okay, cos squared, I'm going to go A plus, I'll let you go x, cos squared x plus sine squared x equals 1, which means one way we can write sine squared x is 1 take cos squared x. Now that's the substitution you're going to perform there. So what we'll have, cos to the power of 3 theta, take 3 cos 3 theta, and here we're performing the substitution. It's going to be 1 take cos squared of 3 theta. Okay, we can distribute this. So we're going to have cos to the 3 theta, take 3 cos 3 theta, take 3 plus, it's going to be negative, plus 3 cos power of 3 theta. And then when we collect like terms, they're like terms. 4 lots, cos to the 3 theta, take 3 cos 3 theta, 3 theta. All right. Is anyone still on this board? So we'll do the last part then. Now, does anyone have any questions about that one? Yes.
Where did you get the 3 theta from? Because in the question it's just one lot of theta.
Yeah, I'm not supposed to write the 3 theta, am I? And so that's carried on the whole way through. Yeah. Yeah, so we were going so well. It's a lot of threes. That's a whole whiteboard marker of threes. You didn't want to tell me earlier?
I didn't want to interrupt you, sir. The process is still there.
Next time, please interrupt. Yeah, the process is the same, isn't it? So, I've missed one. There we go. Okay, so now what does it ask us to do next? Solve the equation 4x to the 3, take 3x, take half equals 0. Okay, so a big clue is hence. Hence, solve the equation. So what we're going to do is pretty creative here. Firstly, let's just get the variables by themselves and we'll move the x over. Because what we can do is we can replace one variable with another variable. Alright, so we're going to let x equal cos theta. Alright, so that's the hence. If x is cos theta, then what we have is we've got 4 cos to the 3 theta, take 3 cos theta. Okay, now we can do that, alright, because cos theta is a variable. That's the only reason we can do it. It's a variable. What it means is it takes lots of possible values. Okay, it's not restricted to one value. Okay, so then if we're going to go through and solve here, now we know what we did before is we proved that this can be expressed as cos of 3 theta. So this whole side collects to cos of 3 theta. It's equal to half. And so then we can look at our unit circle. When is cos a half? It's when the angle is pi on 3 and 5 pi on 3. For now, we're not going to consider multiple solutions. Let's just leave with the first two solutions for now, and maybe we can in a moment. We'll investigate. We've got pi on 9 and 5 pi on 9. Okay. Now remember what we've said. X equals cos of theta. We haven't answered the problem here yet because we're asked to solve what are the values of x that make this statement true. So if x is cos of theta, that means x is cos of pi on 9 and cos of 5 pi on 9. Okay. And because cosine is cyclic, that is, it repeats itself, that means if we've got pi on 9 and we'll have 19 pi on 9, and then the next one, that they are all also going to be solutions to this. So we do need to include the multiple solutions here. So we'll go cos of pi on 9 plus k2 pi, and cos of 5 pi on 9 plus k2 pi. K is an integer. Okay. Now, I'm just thinking out loud here. I think we might need to make a slight adjustment to that actually, because what is the period of this function? So this is pretty complex here. My suspicion is in the textbook they'll accept that, okay, but now because we've entertained the idea that there's multiple solutions, we think about this function and the period of it, it's not too high. Alright, so remember, let's go back, this is a good opportunity for review. Remember, like if we have, that's sine. Okay, if we have cos, that's one wavelength, and you'd have one wavelength in 2 pi. If we have cos of 2, that's cos of theta. If we have cos of 2 theta, that means there's 2 wavelengths in 2 pi. So that would mean we go and we finish there. We go down, finish there, down, finish there. Alright, that would be cos of 2 theta. And then cos of 3 theta means there's 3 wavelengths. And the other formula for period is that period is 2 pi on b. Alright, where b is the coefficient of theta. So in our circumstance, b is 3. So that means our period is 2 pi on 3. So that means my suspicion is we have to go plus k2 pi on 3. We have to add the period there. Okay, cool. So let's have a go at 4e. Should track nicely through it. Come around and see how we're going with everything else.